Those of us who work in the electric power industry all know that protective relaying is an absolutely vital part of the power system. It impacts on all areas of the system: power generation, transmission, distribution, and utilization. Protection is of concern to many different departments and divisions of the power company. The first that come to mind are the relay technicians and engineers, who are responsible for installation and test and calibration of the protective circuitry. Also very much involved are system operators, the operators of power plants, transmission systems, and distribution systems, who need to interpret and respond to the operation of protective relays. The subject is also extremely important to planners and system designers, as the design of the power system depends to some extent upon the protection schemes to be installed, and vice versa. And last but not least, company management is extremely concerned with protection as it affects the reliability of power supply to the customers. If protection schemes do not operate correctly, the result can be extensive damage to power equipment, with consequent high repair costs and perhaps long outage times. It is perhaps a little annoying, if not ironic, to technicians and engineers working in the relay department that when the power system is functioning properly, most of the staff completely forget about protection. However, when upsets do occur on the system, everyone expects the protection schemes to work precisely and initiate action to prevent equipment damage, to prevent injury to personnel, to protect the public, and to reduce customer outage to a minimum. This video program discusses and demonstrates the application of protective relaying in all parts of the power system. We'll be discussing protective schemes and also be looking at different types of relays. The specific design of protective relays varies with different manufacturers, and from time to time, changes and updates are made, especially as solid-state technology is more widely used. Detailed test and calibration procedures for particular manufacturers' relays are thoroughly covered in another video program of ours dealing with relay test and calibration. However, this video program emphasizes application of protective relaying, which remains basically the same regardless of design variations. In this, the first tape in the series, we'll be looking at why protection is necessary, and then we'll discuss some of the general philosophy involved in the protection schemes. As we've mentioned before, protection touches on all parts of the power system. Therefore, in preparing this program, we have to assume that you, the viewer, have a general knowledge of all of these areas, in addition to very detailed knowledge in at least one particular area. In fact, most electric power companies already have our well-known video training programs which cover generation, transmission, and distribution. All these programs include a review of electrical fundamentals. Therefore, this material will not be repeated here. So why do we need protective schemes? Well, the primary objective of all power systems is to maintain continuity of service to our customers. When abnormal conditions do occur, the protection equipment must function so as to reduce damage to the minimum and at the same time minimize the outage time to all customers. But what are the causes of abnormal conditions? Well, they're usually the consequence of one or more of the following. 1, natural events. 2, physical accidents. 3, equipment failure. And 4, misoperation. Natural events which can cause problems to power systems are lightning, wind, ice, earthquake, fire, explosions, falling trees, or flying objects. Physical accidents include such things as a vehicle crashing into a pole, or perhaps animals or people coming into contact with live equipment, or a contractor digging into underground cables. An example of equipment failure would be Say, a breakdown of insulation in a transformer. An example of misoperation would be if the operator inadvertently closed the breaker to energize a line which was still solidly grounded. All of these abnormal conditions will result in a fault. That is, an unwanted short-circuit connection between one phase wire and another, or between a phase wire and ground. The consequence of the fault is usually a dramatic increase in the value of current flowing, and the resultant increase in heat produced in the conductors is the main cause of damage. The actual magnitude of fault current depends upon the amount of power available to feed into the fault. It's also dependent upon the resistance to flow, that is, the impedance between the fault and the source of power supply. The total impedance is made up of A, resistance of the fault itself, B, resistance and reactance, that is, impedance of the line conductors, C, impedance of any transformers or reactors in the circuit, and D, impedance of the generating source. The calculation of probable fault currents for different conditions is a very important task for the system designer. Now, why is this? Well, any switchgear which is installed must be capable of handling the fault current. If a breaker is undersized, it could be completely destroyed when trying to clear a heavy fault current. However, as you know, overcurrent is not the only effect resulting from fault conditions. For example, a fault in a generator could cause serious change to system conditions, such as undervoltage, a change in power and power factor, a change in direction of current and power flow, a change in frequency, a change in temperature inside the generator, physical movement, for example, the generator windings. I'm sure you can think of others, and it's these very changing conditions which allow the relays to sense and detect the presence of a fault. Most relays use one, but often several of these changing factors, sometimes called handles, to determine whether the fault condition is acceptable or not. We must recognize that some fault conditions may be tolerable, at least for a short period of time, but others may be intolerable and require immediate isolation from the system to prevent damage. The protective system must be able to measure and respond to its incoming signals in a very short time period. If the conditions are determined to be intolerable, then the protective system must take action immediately, usually to trip out circuit breakers. Conversely, if the fault is tolerable, then the protective system must not operate. In most power systems, the protective relays are rarely called upon to operate, but under fault conditions, it is absolutely imperative that they do operate precisely and provide the correct action. If a relay fails to operate and hence clear an intolerable fault, then equipment damage may occur, and certainly there would be a system upset. For this reason, it is customary to install additional or duplicate relays to provide backup. If the backup relays are installed in the same station as the primary relays, this is known as local backup. Sometimes backup relays are located at a remote station, and this is called, logically, remote backup. Here we see the fault way out along the line, but the local protection fails to operate. The remote backup will then operate to open this breaker and so clear all of this line, as well as the bus and other outgoing feeders. When remote backup relays operate, they will generally isolate a larger area from the system and so cause a loss of power supply to more customers. The backup relays must be correctly coordinated so that they allow primary protective schemes to operate first. Only in the case of failure of the primary protection would the backup relays need to operate. We'll be looking at all of this in great detail as we proceed through this program. Remember, at this point, we're looking only at the basic philosophies behind protective schemes. At this point, let's take a break, and then we'll come back and look at some simple protection schemes. For now, please switch off the tape and review this material in your workbook.